Hey, AP Chemsters, this is Mrs. Vanderwall bringing you the very first edition of the Blank Wall series. Before we begin, I'd like to talk about the expectations as a flipped classroom and what you should expect as a student. First of all, treat this as you would in a traditional classroom with a teacher up front. So, as the teacher's writing things down, you should be writing things down. When the teacher pauses and lets you think, be actually thinking, be an active thinker at this point. At points, we're going to ask you to solve problems and come up with answers, and we want you to actually do that. Just don't copy things down. Be a smart student and treat this in the manner in which it's intended to help you be a better AP Chemistry student. So just don't sit there mindlessly texting and watching TV and just scribbling down whatever we're writing. You should be in a quiet environment, concentrating on what we're doing. And a true advantage of a flipped classroom is that if you didn't get something, you can always pause it and go back and start again. All right, that being said, let's begin. Chapter 1 is pretty much a review from what you should have learned in your first year chemistry class. And we start off with atoms and molecules. That should hopefully bring back good memories. And so atoms and molecules determine how matter behaves. If they were different, then the matter would itself be different. So atoms is actually from the Greek word atomos, which means indivisible, which means you can't divide. And actually that Greek definition was good for several thousand years up until the late 1800s when J.J. Thomson discovered the electron, the first subatomic particle. So think about how many years that original Greek definition of atoms was really good. So what is this definition? It says sub-microscopic particle. Well, what does that mean? It is smaller than you can see in a microscope, a particle that can be made up into fundamental building blocks of matter. Atoms are made up of only one kind of matter. They cannot be broken down. So what are some examples? Well, I'm going to put up here is my example. I'm going to call that hydrogen, and I'm going to call this oxygen. I'll call this carbon. Now, notice what I tried to do here. Are those atoms the same or are they different? And besides the color, hopefully say, yeah, there is still something different about these atoms, and obviously it has to do with size. So the hydrogen atom is pretty small, the oxygen atom is next small, and the carbon atom is actually a little bit bigger than the oxygen atom. So what sort of things could explain this change? Well, if you think about what's in an atom, we can talk about electrons, neutrons, and protons, and their attractions as well all play into the size. So these atoms are different, so it makes the matter different. So hydrogen is different from oxygen, as you know. What about molecules? Molecules are atoms that are bound together in a specific arrangement. So they're made up of more than one kind of atom, and they can be broken down by chemical means. So for example, I have over here, we have carbon dioxide, and we have our water. Well, what's carbon dioxide made up of? It's made up of the carbon, right here, and two oxygens in a very specific arrangement. Carbon dioxide would not look like, moving this oxygen to one side. It's a linear molecule. It's the only thing it can be. Over here, water is made up of one oxygen, here it is, and two hydrogens in a very specific arrangement. Now you can break down a molecule. A very simple experiment is electrolysis. You can put electrodes into the water, and the hydrogen gas will be formed at one end and the oxygen gas is formed at the other end. So you can break down a molecule into simpler arrangements, in this case into their elements. Okay, let's go on. Scientific method. We can talk about theories. Theory is a hypothesis that are assembled in an attempt to explain the why, the what that has happened. And the model, there's many different models out there. There's many different scientific methods out there. There isn't one correct method to do science, actually. So this is just one version of the scientific method. What is really all scientific method models start off with is an observation. And from there you might be wondering, well, why is that happening? So then you develop a hypothesis. And from there you want to do some experiments. Do your experiments confirm or reject your hypothesis? Either way, you should keep testing. Notice this is a loop. You don't stop testing. And eventually, you're going to come up with a theory. This is your why is this happening? And again, you'll probably do some more experimentations. And again, it's a loop. You don't ever really quit. So your theory explains the why or the what of the hypothesis. So what about a law? Over here is your law. What's going on here? Your law is actually just based out of your observations again, and you're forming relationships. And perhaps you can, from there, derive a hypothesis from the law as well. So I like to think of a law as, let's say, Newton's laws. F equals ma. There's one of them. So that law describes the relationship between force, mass, and acceleration. Notice it's also an equation. Laws are typically in an equation form. E equals mc squared. That's your law of relativity. There you go. You're showing the relationship between energy, mass, and the speed of light. A theory doesn't have that equation to it. It's just explaining, like the atomic theory is explaining how the atom is arranged and how it has changed over time. So why don't you take a few minutes out, pause this, and answer problem number 1. So pause this, answer it, and when you're ready, come back. All right, so which statement best explains the difference between a law and a theory? Hopefully from my explanation, you got the answer B, as in boy. Law summarizes a series of related observations. That's your relationship again. And the theory gives the underlying reasons. That's your why and your what. So go ahead and pause this, read over problem number 2, come up with your answer, and then come back and we'll explain it. All right, so problem number 2, the answer is actually B. They're asking you, so we have an atomic theory or the law of gravity, so now they're saying, should the law of gravity actually be changed to a theory of gravity? And the answer is no. Scientific laws are based on summaries of these many observations. They're the relationships. And you have observed gravity over and over again. You're not explaining the gravity, you're just making these observations between the relationships. So keep it as the law, please, and your answer is B. Now, if you had answer A or C or D and you want further explanation, ask your teacher tomorrow. So I would be happy to answer that for you. Let's go on to the next page. Classification of matter. Again, this should be review. You've probably done this ever since you can remember. So let's just spend a couple minutes and then go on. So here we have 3 beakers. Hopefully you recognize this is a solid, liquid, and you don't see anything, so it's a gas. And what's a solid? It's rigid. It has a definite shape and volume. Now, there's something that you might not be aware of. Molecules are close together, okay, but what are they doing? They're still moving. They're still vibrating around these fixed points. And it says it's virtually incompressible. So let's look at the picture I just drew here. Notice I have these circles again. Those circles are representing the atoms of the solid. They're very close together, and they are still moving. They're still motion. I don't know if you are aware of this, but only at absolute zero, which we have never achieved. We've gotten close, but we've never been to absolute zero. That's the only time, or the only temperature, if you will, when theoretically all motion stops. So if you are at 1 degree Kelvin, 1 Kelvin, then it is moving. How is it moving? You mean your table's moving, your chair's moving? And the answer is actually yes. The molecules within them are vibrating around these fixed points. Notice there's not a lot of space between my solid or my atoms that make up the solid, so there isn't a whole lot of extra room. There's not a lot of empty space in which to be able to compress the atoms. All right, what about the liquid? Has a definite volume and takes on the shape of the container. So here's my liquid. Not a very good picture, but it's the best I could do. These molecules are vibrating, so they're like going back and forth. But they also have rotation, like they're doing flip-flops, if you will, and translational motion. If it is a molecule with bonds, and you can talk about how those bonds themselves are moving in a sense within that molecule. But what else should we know? That these can slide past one another, so they are moving. They are not fixed. but they're still fairly close together. There's not a whole lot of space, so a liquid is somewhat compressible, but still not very much. Now I want to do something, and I want to still show this idea of motion, that here, these, I'm going to call these little zoomies, all right, little things to show that these molecules are moving. All right, so they are moving, they're going past each other, they may be knocking into each other. All right, so those little arrows are representing motion in a sense, and I'm not going to put any around the solids because they are vibrating, but they're not sliding past each other, so I'm going to leave those alone. So what about a gas? All right, let me scroll down here. A gas has no definite volume, hopefully you figured that out, and it does again take on the shape of the container. So here's my gas, and they're still vibrating, they still can rotate, and they are independent. That means they don't have attraction for one another. They are highly compressible because look at all this empty space between the molecules, or the atoms at this point, and they're very far apart. So let's talk about the motion. Do you think that these gas molecules are moving faster or slower than liquids? Think about it. All right, hopefully you said they're faster. So how do you think I could show this kind of motion using what I call, there's no scientific term for this, but my little zoomies? All right, should I put one little zoomie here? How about two little zoomies? In a sense, I'm trying to show you, well, that would be about the same motion as a liquid. So I'm going to add another little zoomie here. All right, showing you that these gas molecules are going even faster than the liquids. All right, so that's my scientific term there, zoomies. All right, so we have one more term here, vapor. Vapor is a gas phase of a substance that is normally a solid or liquid at room temperature. Kind of like if it rained and you have a puddle outside, what's going on there? Well, hopefully you know that it's not boiling outside, so those liquid molecules are still going to evaporate into the gas phase. All right, let's go on and talk about mixtures. Mixtures can be physically separated. You have two or more substances put together. Okay, that would be a mixture that you can physically separate. You can take tweezers and pull them apart. That would be a mixture. Like, cinnamon and sugar, you can, physically tweeze them apart if you really wanted to. So we have two ways of describing mixtures. One of them is called homogeneous. Homogeneous, the prefix homo means the same or alike, and so this mixture has has visibly indistinguishable parts. I mean, I can't look at it and say, oh, I see two phases. I can see two different things in this mixture. Solutions including air. Well, that's a good thing because I can't see the air, the oxygen in one part of air and the carbon dioxide in another one. I'm assuming that here, where I'm sitting right now, has the same amount of oxygen in the air as if I went someplace else. Okay, that would be a homogeneous mixture. So why don't you pause this, come up with a couple examples of your own, and see how they compare to my examples. All right, so my first example, you may not have come up with this, is brass. Brass is a homogeneous mixture of copper and zinc, two solids. Can I take them apart? Well, how can you separate two metallic solids like that? What physical property might I take advantage of to separate out the copper and the zinc? If you said melting point, that's probably the best one. All right, best idea there to separate it out. I had another one maybe you came up with is rubbing alcohol, isopropyl alcohol. You buy it at Kroger's if you want. Actually, when you buy isopropyl alcohol, rubbing alcohol, it is a mixture of pure isopropyl alcohol and water. So it's been watered down, it's been diluted. So can I separate the alcohol and the water out? They're both liquids. So how would you separate out liquids? What physical property would you use to separate? Well, if you said boiling point, then you had a good answer there. And of course, because it's me coming up with these, I have to get chocolate in my answer somehow. So milk chocolate would be a homogeneous mixture. I cannot see the different parts layered together. It all looks and tastes the same yumminess. All right, so that'd be a homogeneous mixture. So heterogeneous, hetero, the prefix means different. So these are different phases in a sense. They have highly distinguishable parts. I can tell the phases apart. I can tell where the different things are. So why don't you come up with your own heterogeneous and see how you do. All right, so how'd you do? I came up with sand and water first. It's the first day back. You may be missing the beach. Well, that would be a heterogeneous mixture. Probably a lot of you may have come up with Italian dressing. Probably one of the most common examples, oil and vinegar. They don't mix, they form different phases. And of course, keeping in mind, you probably saw that pecan earlier, Mr. Goodbar, there's peanuts mixed in with the chocolate. I can see the two different things apart from each other. All right, real quick, here is some apparatus to tell the different, how can I physically separate these. Here's distillation. This is the setup. If you want to separate your rubbing alcohol, you'd put your mixture in here, you're boiling it, and the one with the lowest boiling point, which I think is the alcohol, would be down here, and the water would remain behind. Here's a filtration. That's if you have a solid and a liquid. So if you want to separate your sand and your water out, your sand would be in the filter paper, your water would come through. Folks, we're almost done. Let's go to the next page. All right, so we talked about mixtures. Well, let's talk about pure substances. Pure substances can be pure compounds or pure elements. So remember how it sounds like what we just talked about on page 1. We talked about atoms and molecules. So what's the difference? Why aren't we saying the same thing? Well, a compound is, two or more things that are chemically combined that can be separated into elements by chemical means. A molecule is a single unit of a compound. So if I have water, which is a compound, a single unit of water is the molecule. So you can stick water, you can write water down here if you want. You can write carbon dioxide down here if you'd like. So again, a molecule is just a single unit of that compound. An element, folks, there's 118 known elements. Every single one of those have now been created and discovered. So the entire periodic table right now fills up that last row. So those are your elements. They cannot be decomposed into simpler substances. You can separate them into their electrons, protons, and neutrons, but that's not what we're talking about. It doesn't retain its chemical properties or its physical properties. So my example can be hydrogen and carbon again. So what is the difference between an atom and an element? Well, an atom is a single unit of an element. Okay, you can also add cobalt, which is Mrs. Buchanan's favorite element because of its beautiful blue color. And you can also add here vanadium, which is my favorite element. Remember, I'm Mrs. van de Walle, vanadium. And vanadium is actually named after the Norse goddess of beauty, Vanadis, if I said that right. So, van de Walle, goddess of beauty, vanadium, it all kind of goes together, doesn't it? So why don't you go ahead and, using the terms that we just learned, start putting this stuff together. So organize this dichotomous case, see how you do. Pause this, and I'll be back. All right, well, let's see how you did. I'm going to put matter up here because that's everything that, has mass and takes up space. All matter can be divided into pure or mixtures. Okay, this is the same chemical composition. The same composition. This has actually a varying mixture. So if you make your sugar and your cinnamon for your yummy, cookies or something, you can add more sugar whenever you want it and less cinnamon. It has a variable or varying composition. Pure substance, you can't say that. So then you can break these down into different things. So an element cannot be broken down into simpler substances, but a compound can. Heterogeneous is not uniform throughout, while homogeneous mixture is. And you can look at their examples below here. So an element, I think they're going after helium, which is made up of the Goodyear blimp. Compound here is my water. Notice these are all the same. Every single one of these molecules are identical. It's a pure substance. Here's my heterogeneous, my sand and my water. Notice that these are different than these. We have a definite layer going on. That's your heterogeneous. Your homogeneous, they're saying, is tea with sugar. Can I see the layers of my tea? No, I can't see where the sugar molecules are. They're in there. I know it's sweet. So it's evenly mixed throughout, and so that would be a homogeneous mixture. Now before I go, I would like you to look over the next page, problem 3 and problem 4, and come up with ideas before tomorrow. So I am done. 20 minutes are up. I went a little bit over. I apologize. Hope you have a good evening, and we'll see you all tomorrow.